Thank you. Thank you very much for introduction. And thank you again for Juan and organizers for this very nice workshop. I really enjoyed. I mean, I already enjoyed the summer school last week, and then this is actually my fifth talk here. But so that's one reason. But I mean, so I would apologize for some of you that they probably you have heard already this kind of talks a few times. Hopefully, not more than a few times. But so I mean, so last week I couldn't say anything about the Ramsey theorem. So but I mean, in my talk, I mean, many. Sure, sorry. I mean, yeah. So today, I mean, I'll try to give a more like a general survey what's going on the recent studies of the first order strengths of Ramsey theorem for pairs, and then, well, introduce some recent results. But recent means still already 3-4 years already. So yeah. And okay, I'll try to start. Okay, so well, I'll try to just start very basics. I mean, because this is just a survey part. So so here's the subsystems of second order method we mainly deal with. So actually today I will just think about LC0 star WK0 star LC0 WK0 AC0. But just mid-3 are the major things for today's talk. And I won't give any detailed definitions of those things. But and then, okay, for the strengths of Ramsey theorem in the setting of second order method, it's formalized in this way. I don't mention precisely, but I mean it's well known that it forms a hierarchy. I mean LT1 2 is provable within LC0, and LT1 is stronger, LT2 is stronger, LT2 is stronger than that, and so on. And what very well known is that so there is a computable coupling on n tuples from natural number to 2, which has a which always for any computable coupling pi n homogeneous set exists, while already for triples there is a computable coupling whose homogeneous set always computes zero jump. So that means that the AC0 proves the RT and K for all standard n and k, while over RC0, RT32 implies AC0. So the hierarchy is something like this, and then so the hierarchy essentially stops here, and the rest is just AC0. Yeah, well, actually, this is just over RC0, and over RC0 star, the behavior is very much different. I don't think I have some time to mention those things today, but yes, that's also an interesting topic. And on the other hand, so the intermediate things like RT1, RT2, RT2, the situation is much more complicated. And then, RC0 plus induction doesn't imply LT22, well, even WK0, but that's more difficult. And then, you have to think about the more like the corner avoidance kind of thing. So this is more like so the low basis type of thing. And then corner avoidance theorem shows that the RC0 plus RT22 does not imply AC0, and then you can prove it actually from the Churchill-Strayman's result for the low two basis theorem for AC0. RT22 also supports this result. And then the PAD clear avoidance is a lot harder, but we can do that. And then RT22 indeed does not imply even WK0. That's recent result. And then separated, so I won't say the definitions of the SRT22, but if you decompose RT22 into COH plus SRT22, then separation is harder. And then So this separation is just known recently, especially on omega model and so on. So that's the, anyway, together with combining the, well, I'll explain the first order translator, but together with some extra information, we may say this picture. So the RT12 is just provable within RC0 and WK0 is just incomparable. I mean, I always forget not here, but incomparable with all these things. And then RT32 is equivalent to AC0. And so, what about the first order consequences of Ramsey several pairs, which is the main topic for today? And over RC0, it's not, I mean, just without that the RT1 is equivalent to B sigma 2. And then for the case n is bigger than 3, of course, the RTN2 it's just equivalent to ACA0, which is a conservative extension of PA. So then the main question is, what are the first order consequences of Ramsey several pairs? I mean, essentially just RT22 and RT2. And again, by Jeff, over RC0, it's known that RT22 implies B sigma 2, while RT2, Ramsey several pairs with arbitrarily many colors implies B sigma 3. So that's the traditionally known result, I would say. And then to obtain the better upper bound, then, well, so from the newer perspective, I mean, modern perspective, I would say many conservation theorems after this were obtained more or less from the, well, we call just LLM basis theorem, but probably weakly low, not the weakly low as well, I mean, basis theorem. And so, okay, so here, I mean, x is, below, m plus 1 below y means that just m's jump of y computes a complete PA degree relative to, I mean, PA degree relative to m's jump of x. And then, so fix this notation, and then weekly OM basis theorem or LM basis theorem says that, well, okay, if gamma is of the form pi 1, 2, then basis theorem for gamma says that, okay, for any z and for any set x, such that, well, x is weakly relative to, I mean, right, yes, x is below z, then there's this delta zm set y, I mean, m's jump of z compute, m minus 1's jump of z compute a set y, such that, well, okay, y is the solution for this statement, and the join of x and y is still below z in the sense of below m. That's the definition of basis theorem. And then okay, so then, well, that type of low basis theorem behaves very well together with the models of second order arithmetic. So let's say, assume that RC0 plus I sigma 0 n, or like RC0 plus B sigma 0 n, proves that some weakly OM basis theorem for gamma, and then m is smaller than n. Then we always have the following. Start. So for any countable model ms of RC0 plus I sigma 0 n, or B sigma 0 n, which is topped, let's say. Topped means that there is a element in the sense of, I mean, top element in the sense of doing reduction. Then there exists a expansion of that model, S prime, extension or I mean, you may consider second order part as a predicate and it's expanded. I don't know which is the right word, but I mean extended and expanded S prime such that M and S prime is a model of, well, the same level of induction together with gamma, the same level of bounding together with gamma. That's possible. And, well, okay, it's kind of classically known if the, well, M is strictly smaller than N, and this basis theorem is more like a pure, like a low basis theorem or low M style basis theorem, then just definable extension is good enough. And then, well, actually, that can be weakened to the more like a weakly low type basis theorem by the conservation result, or I mean forcing argument by Simpson-Smith or Harrington's conservation proof, plus the Beranger's formalized jump inversion theorem, which is available within B sigma 1 even, B sigma 1 plus exponential even. And okay, so I mean, if you know kind of a basic thing about the pion conservation, this type of construction, of course, provides a general conservation theorem. This way. So okay, so the previous theorem almost says this. I mean, if like RC 0 plus I sigma 0 n or RC 0 plus B sigma n implies weakly low M basis theorem for gamma, then that statement gamma is found conservative over RC 0 plus I sigma 0 n or corresponding B sigma 0 n. And so from this perspective, like Schwarzschild-Simon's result, I mean, and one of the most famous paper by Peter, probably, I think. But I mean, I really love this paper, and then my students still always start reading from this paper. And then, so it says, okay, well, RC 0 plus I sigma 02 proves VQO2 basis form for RT22. Well, so originally, it's not in this form, but we can reformulate the proof this way. And then, so RT22 is found conservative over RC 0 plus I sigma 02. And RC 0 plus B sigma 02, actually weaker than I sigma 02, already proves the similar level basis theorem for CAC or ADS. And that's essentially what Chon, Yang, Steinman did in their conservation proof. I mean, so it's not written in that way, but I mean, if you read it, this terminology, and that's available. And we can do the same thing for a RT2 over B sigma 3. So that's, but the paper itself is it's my result with Ted Simon, but the paper itself doesn't mention in this way. But I mean, we can reformulate the proof actually. I mean, that's actually what the co-author of this, so the collaborator, so one of my students, Hiroyuki Ikari, did very carefully formulating the basis theorem within B sigma 3, and then so we now know it. Yes. So, but still, we don't know, kind of a really famous open question, whether RC 0 plus RT22 is found conservative extension of B sigma 2 or not. This is still open. The answer is yes, if RC 0 plus B sigma 2 proves the weakly low to basis theorem for RT22. I mean, so the provability is actually enough to show the conservation. And I would say later that, well, actually, this is if and only if, but I mean, so I don't explain the details for that. But yes. Yes. Yes, this is tight result. I mean, so the first order part of RC 0 plus RT2 is now fixed, I mean B sigma 3, identified. Yes, so for RT2, this is the kind of a true information, while for RT22, it's still difficult. And then so this question is, I mean, widely open for long. I mean, posed in George Steinman's paper, and then open for a long time, and then still, I mean, it's ongoing. But so another approach for that is using more like a order analysis. Yes. Oh, that's already a question, I would say. I mean, so B sigma 2 is, of course, one important consequence. And then whether there's more thing or not, it's that question in a sense, right? I mean, okay, so actually, well, so it's not a consequence of the previous discussions, but actually one of the most important, first of the consequence of RT22 is this one, basis theorem for RT22. But I mean, this is actually very sensitive, but the RT22 plus RC0 proves that the basis theorem for RT22, which is not trivial indeed, I mean, so RT22 itself does not directly imply that there is a something like row 2 type of solution. There's no information about, there's no direct information from RT22, but actually that's known. RT22 over RC0, RT22 implies that the, well, weakly 2 basis theorem for RT22, meaning that for any computable instance, you'll find a weakly row 2 solution for that. That's accidentally provable within RT22. Solution doesn't help, actually. But, yeah. Mm-hmm. You mean like C sigma 2 or those things? Well, so I don't think the TED provides a kind of a example stronger than B sigma 2. There are many intermediate statements between B sigma 2 and I sigma 1, and some of them are related to like rainbow Ramsey theorem and so on. But above the level of B sigma 2, I guess there's no known famous kind of a intermediate statement. Well, I mean, between B sigma 2 and I sigma 2. Right. We may add P sigma 1 in there, but I mean, I'll talk about it a bit later. But yes. Yes. Yeah, feel free to ask me. You mean my guess to this question?
Yes or no?
I don't know. I mean, still, it's very hard to say. I mean, I lean toward one side sometimes and then the other side some other time. So, but I mean, yeah, okay. So as a consequence of this talk, I would say some kind of isolation about this question. Sorry. Yes. Mm-hmm. Mm-hmm. Yeah. Well, those statements actually has a very important connection to the first order consequence of RT22 over RZ star, indeed. But sorry, not the scope of today's talk. I'm sorry, but yes, but yes. Yeah, well, I will say something about this later.
Also, that's interesting too.
Yes. That's actually the main scope of this talk. Sorry. Yes. So I believe they are kind of a reasonable related question to the original question. Okay, so I'll try to continue, but well, let's first focus on this one. So what is the consistency strength of RC0 plus RT22? And for that, actually, using some basic order analysis, or in some sense, it's more like a indicator style argument. And then what we can do is that, okay, we can approximate the size of the solution for something like Price-Harrington version of Ramsey self pairs in this sense. So meaning that to obtain the solution for Price-Harrington for pairs in two colors, but we want to obtain so-called omega to the k large solution, then what we need is the original set has to be this large, omega to 300 k large, which is actually, I mean, not that big, actually. I mean, almost the same order, I would say. I mean, just the same order type level. So that's the important information. And anyway, so this means that at least the Price-Harrington part for this type of largeness is all provable within RCA0. And then combining this together with the kind of a general type of indicator style argument, then we have actually RCA0 plus RT22 is at least pi3 conservative extension of RCA0. But originally, well, without this kind of calculation, but with Ludwig, we did more like a more complicated discussions. But in the end, okay, some ordinal analysis type of calculation is good enough to show this. That's now what we know. And on the other hand, well, just recently, I mean, the paper is not yet published, but so we know that RC0 plus RT22 is indeed pi04 conservative extension of RC0 plus B sigma 2. Here, we can add B sigma 2 as well, but I mean, well, RC0 plus B sigma 2 is just a pi3 conservative extension of RC0, so it's actually the same. But, well, of course, the B sigma 2 is the kind of a typical pi04 consequence of RT22, which is not provable from RC0. So this is, at least for the level pi04, it's tight. So RC0 plus pi04 part of RC0 plus RT22 is B sigma 2. Pi3 part is, this means I sigma 1, essentially. So that's what we know. And anyway, I mean, its consistency strength is just the same as I sigma 1, which is the level of PLA. So that's what we know. Okay, and then we may add some like proof-theoretic strengths at least. That's another type of discussion. And so so we may consider that the so-called action BME, which, well, I mean, originally it's a combinatorial statement, but I mean, now it's known to be equivalent to well-foundedness of some ordinals below epsilon 0. And well, so originally, so when Chon-Yan Sleiman constructed a model of RC0 plus RT22, which I sigma 2 fails, then their construction is something like this. But I mean, so this BME itself is already a kind of a informative part of the constructing models. And on the other hand, we can always preserve this type of well-orderedness as well. So together with BME, well, okay, so RC0 plus RT22 plus, well, oh, sorry, so no, I mean, what I wanted to write is, so here actually the second, essentially, I mean, sorry, so the people name is the wrong, I mean, yes. Yes, okay, yeah. Fine. Yep. Yes, so the I sigma 2 and B sigma 2, its pi 4 part is different. Well, actually, pi 1 part is different already because the I sigma 2 proves the consistency of I sigma 1, while B sigma 2 does not. So that's the main difference. Yes. So yes, so this proof also, I mean, separates I sigma 2, I mean, isolate I sigma 2 from, I mean, RT. Which one? B sigma 2, yes.
B sigma 2 is already pi 4.
B sigma 2 itself is pi 4, so yes. I don't
Like RC0, C sigma 2.
Yeah, C sigma 2 is yes. That's the original counterexample by Ted, I think. C sigma 2, kinetic statement.
There's no sigma 2 injection from the entire natural number universe to a bounded state. Very poor math.
Yes. Okay. So I mean, so we may add actually the like proof-theoretic difference or well-foundedness of all now. Then okay, well actually we know. I'm sorry. So I'll try to say it again, but this is by resetting myself. But I mean,
theorem,
right.
Analysis of Chomsky-Yang.
Yes, almost hidden consequence of Chomsky-Yang construction. And then recently we upgrade this to the pion conservation level. So at least if we add all the well-foundedness of owners below epsilon 0, then indeed pion conservation is true.
Yeah, and the names are correct in that.
Mm-hmm.
Yeah.
Yes. Yes. So that's one of the recent progress. Yes. Below epsilon 0. Yes, just there's a scheme.
And it's important. It's not a finite state.
Scheme, yes. Or pion 1 statement, essentially. Okay. And then, okay, well, I won't say much about it, but there is a so-called WK0 star isomorphism theorem, which is originally for WK0 star plus not I sigma 1, but we can consider a similar thing for the level of B sigma 2, and which says that, well, given a model of RC0 plus B sigma 2, but I sigma 2 fails, well, actually, you may add parameter here, but I mean, just for simplicity, I just write in a light face version. But you can always relativize this result, and then well, what's that? So okay, yeah. So this is well, yes, yeah. And then A is something like a cohesive degree essentially. A is cohesive degree, and then there exists a model S tilde such that, well, okay, so I mean, for every x in S tilde is just sigma 2a definable, or delta 2a definable indeed, from this single cohesive degree A. But cohesive means actually the induction is violated, so the meaning is kind of sensitive, but yes. And actually, so weakly low in the sense of our model. And on the other hand, so this model is isomorphic to the original one. So original one, of course, there's no complexity assumption. Second order part is anything. But indeed, so take just any model, then in a sense, it has to be bounded by some fixed real, which has a degree, which has a cohesive degree. So that's the idea of isomorphism theorem. And from this result, actually, because so if a model of RT22, always it's a model of B sigma 2, and if in that model, if I sigma 2 fails, then this situation has to be true. Meaning, yeah.
Is it really the case that and S are isomorphic?
Well, I mean, so this can be true. I mean, yes. So it's delta 2 closure. It's just always isomorphic. So you can find some substructure from it. So all elements are just bounded. That's the information. No closure property is assumed. So yes. But anyway, so this means, okay, in this model, if RT22 is true, then that means the solution has to be bounded by this A. That's the reason why I mean, so I said RT22 actually implies the basis theorem for RT22 as well. Together with the information that I sigma 2 is already strong enough to prove the basis theorem for RT22. So if I sigma 2, if you have I sigma 2, you can prove the basis theorem for RT22 in the usual way, just formalizing CJS construction. Or if I sigma 2 fails, then all model has to be weakly low 2. So weakly low 2 basis theorem is still true. And so that means that, well, okay, so this means that RC 0 plus RT22 proves the weakly low 2 basis theorem for RT22. And because this is first order consequence, I mean, this is first order statement, because I mean, the solution is just kind of a definable set. It doesn't say anything about the existence of internal set. So this is Pylon statement. So this is a kind of a, well, new kind of important example of the consequence of RT22. And then indeed, we can say that that's the strongest Pylon consequence. Meaning that RC0 plus RT22 is a Pylon conservative extension of B sigma 2, if and only if B sigma 2 itself implies this basis theorem. Because this is the consequence of RT22, and if B sigma 2 implies basis theorem, then, well, general basis theorem versus conservation style discussion. Yes, which is, mentioned here actually, but sorry. Yes. And if you focus on the complexity of this pi1 statement, well, actually it's a pi05 statement indeed. It's an arithmetical statement. The complexity is pi05. So that means that if RC0 plus RT22 is a pi05 conservative extension of B sigma 2, then it has to be pi1 conservative extension of B sigma 2. Because of this killer example. I sigma 1, but that never happens. Because this itself implies B sigma 2. Right. Yes, this is a kind of a stronger counterexample of B sigma 2. What? It's not known whether it's found conservative over B sigma 2 or not. That's open. But I mean, we can isolate the question in this way. So the conservative, if it's conservative, then this basis theorem is already provable from B sigma 2. And if it's not conservative, this is the counterexample. This is the counterexample that why RT22 is not pi1 conservative over B sigma 2. Yes. Yeah, so that's our partial answer. I mean, yes.
You're saying that L2 basis theorem is an important first order consequence, and that there are no other approaches.
Right. So that's the strongest one.
Negative answer, basically.
That's the strongest counterexample. So we already know that it's the strongest counterexample. I mean, if it's the counterexample, it's the strongest counterexample. Okay. So yeah, so that's the story of the essentially the first half, which is well. So I didn't say anything about the proof side and so on, but so far just about the conservation. That's the survey of the known results. And then okay, so now. How much time?
It was like 21.
Okay, that's definitely good enough for me. Okay, so now I mean, try to talk a bit about the more like so once you know the conservation result, then of course that means okay, if stronger system proves something, then the weaker system proves the same statement. And then okay, how the proof goes on. I mean whether the stronger theorem would help to prove the theorem, whether a stronger system helps to prove the theorem in an easier way or not. That's a natural question. And so that means, okay, so the question is, are there any kind of polynomial proof simulations for the previous conservation theorems? And that's the next question. And so, okay, so to answer to that question, I mean, I'll just briefly review very basic stuff, which is on like proof theory or just general basic study of logic. So because I mean to find some proof transformations, well, the easiest way is just constructing internal interpretation, definable interpretation, constructing a model of some target theorem within your system. That's the basic one. And so the idea is, okay, so for those relative, so-called, usually called relative translation. Relative translation, of course, means that you would give a definition of domain and then like a interpretation of all predicate symbols and then, well, just give a usual definition for relativization. And then the idea of usual relativization, or I mean, relative interpretation, well, the use of it, the main use of the relative interpretation is, well, come from essentially proving the soundness theorem. Right? I mean, so if some interpretation, some relative interpretation is given from, well, from T prime into T. And then, okay, so if T prime proves something, that means interpretation provides the information that how T proves the translated formula. And that's essentially just following the usual proof of soundness theorem. Or, yeah, usual proof of soundness theorem for usual, I mean, first order semantics. And, well, typical corollary is, of course, the relative consistency. And we can upgrade this discussion for the level of conservation if the interpretation is somewhat reflective. Reflecting means that, okay, well, I mean, let's just assume that, well, just the, I mean, T and T prime just share the same language. That's the easiest situation. If they share the same language, and then we can compare the translated formula and original formula in the system we would do interpretation. And so the interpretation is said to be deflective for gamma. If for any gamma sentence or gamma formula C, well, so the translated formula C tau implies the original statement C. If this happens, then we say it's gamma reflective, and then now this provides a conservation result. So if there exists a relative interpretation of T prime in T, which is gamma reflective, then T prime is just gamma conservative over T. Well, just because of the, connecting soundness theorem plus deflection, then we have, okay, if T prime proves something, then T prime proves C tau, then T prime proves C, then T proves C tau, but C tau implies C itself, so T proves C. So that's the conservation proof. So we have conservation result. And moreover, that argument is just very effective in the sense that, well, there is we can consider it as a polynomial proof transformation, polynomial proof simulation. Well, but I mean, to say that, well, okay, the needed condition is actually, so reflection part has to be proved in a right way. I mean, so the theta tau implies theta should be short enough. But in most reasonable relative interpretation, this is almost always true, I would say. I mean, for the case we want to use, for example. And then, okay, so the previous conservation result actually upgraded to this style. So if there exists a polynomial relative interpretation of T prime in T, which is polynomially gamma reflective, then T polynomially simulates T prime with respect to gamma consequences. I mean, so there is a polynomial time procedure to convert proof from T prime implies theta to T implies theta. And typical example of that is, well, interpreted RCA 0 within I sigma 1, for example. Interpreted RCA 0 plus I sigma n within I sigma n, just by considering the definable internal second order structure by just, I mean, mimicking second order object by its index as a sense of computability. That's the idea. But this is actually good for just interpreting RCA 0. But if you want to do the same thing for like row 2 or row 2 sets, then the situation gets more difficult. Because, like, for example, if you collect all row 2 sets, then it's still a model of RCA 0. But I mean, you may violate some induction because there's even for row sets, if you randomly pick 2 row sets and then take a join of those two row sets, it may be not row already, right? I mean, so it won't form the Turing ideal. So this construction is good for all computable sets, but I mean, for like row sets, for example, already we need some adjustment. And for that, okay, we try to do Faustian, essentially. Or in other words, I mean, what we usually use Faustian is actually can be considered as a more like again relative interpretation, but I mean not kind of a classical first order semantics, but actually more like cryptic semantics for intuitionistic logic. So that's the idea here. So the cryptic semantics for intuitionistic logic is, well, I mean, I assume you know at least the basic definitions. I mean, it's just defined like this. And then, okay, so here actually plus means that the word K, well, something is true in the sense of intuitionistic setting, or false in the intuitionistic setting. I mean, so there are two famous things are known. I mean, so of course the cryptic semantics is sound and complete for intuitionistic predicate logic. And also we know that if you take a negative translation of some statement, then it's classical. So meaning that if we define a new relation, well, usual forcing relation, by, well, K forces C fundamentally if K strongly forces the negative translation of C, usual sense. And then this is just the usual definition of our forcing, more or less. But the point is, okay, so then okay, so following the usual soundness proof or completeness proof for quickie semantics for intuitionistic logic, we may still have this, like, I mean, T proves C, well, okay, if and only if, well, any quickie model satisfies C. That's the classical logic version of quickie semantics. And now, okay, let's do relative interpretation using quickie semantics. The idea is just the same as usual definable interpretation, relative interpretation. But instead of using first order semantics, we'll use the quickie semantics, meaning that, so we will define a partial ordered set and then the domain and the relation on each word one by one, just by formulas. And then give a interpretation based on the usual semantics for the quickie models. That's the forcing translation, I would say. Forcing translation, forcing interpretation. And then, okay, so now, yeah, well, okay, to say that it's the right interpretation, now we need some basic conditions for quickie models. I mean, quickie models, well, it has to be monotone, and binary relation has to be the partial order, and so on. So that's needed. But essentially, with the same ways as the relative interpretation, we can define formally something is a forcing interpretation from T prime into T. Just it's an interpretation. And then, okay, now formalized version of soundness theorem is also available. This is again essentially formalizing the previous soundness theorem for quickie models for intuitionistic logic plus the double negation translation part. Formalizing all those things, then we have that, well, if tau is a forcing interpretation of T prime in T, then T prime implies theta implies T proves the theta is false. It's, I mean, still the same as usual, general forcing discussion. Just exactly the same. And then we can also consider the reflection. Reflection. So yeah, the idea is just the same. I mean, something is false implies the original statement. It's provable within T, then forcing interpretation provides a conservation proof. Exactly with the same way. And of course, as the previous discussions, if the reflection is provable in a polynomial way, then we get polynomial proof simulations. So that means, okay, so now go back to our conservation proofs. And then conservation proofs done through basis theorem. So if we can formalize the kind of a forcing interpretation for general basis theorem, that's good enough for all proof simulations. And that's the idea. Well, I mean, I would say that, for example, when I asked like Ted Slayman and those people, and then, so they thought that, I mean, if there is a low-end basis theorem or those things, and the conservation proof is available from those things, then that's already almost certain that one can extract the proof transformation from it. But I mean, how it's a bit annoying. I mean, it's not so straightforward. For each statement, like for WTL0, we can do that definitely. But I mean, for RT22, for example, forcing is already not kind of uniform and so on, and so there's some difficulty. But actually, now we can do that. So the idea is kind of simple, actually. So here, for simplicity, we just deal with low-end sets. But actually, we can generalize it to, I mean, weak low-end kind of thing. Well, there's some other technical details actually for that, but I mean, I don't want to mention today. But anyway, so the idea is that, okay, now we will consider, so second order part is just given by all low n sets or low n minus 1 sets. And then partial order on it is the Turing reduction. So consider second order part is all like low n sets, and then consider it at the same time, that's our post set together with the usual Turing reduction. And then, okay, so now at each point, so this is actually a code for low n sets. So at each point ES, okay, we always believe that our world, our second order object is confirmed just it is Turing reducible to your condition. So consider that post set. Then, well, I mean, I won't say the details, but one can easily, I mean, it's more like routine to check that this Fawcett interpretation is polynomially pi1 reflecting. I mean, because just because the first order part is just the same as the usual one. So like a usual pi1 conservation proof. Well, why pi1 conservation proof holds? Because we don't touch the first order part, so the meaning of the first order statement is not different. And so we can always do the kind of a similar discussion for this interpretation, and then so the interpretation provided by all low n sets is polynomially pi1 reflected over CSO. That's always true. But then the previous basis theorem implies conservation can be upgraded to the basis theorem implies polynomial simulation. I mean, Fawcett interpretation exists. Polynomially reflecting Fawcett interpretation exists. Because I didn't say how we can convert low m Fawcett to weakly low m Fawcett, but believe me that we can do that actually. And then if we assume that, then okay. So the proven basis theorem for theta, then yes, that's the Fawcett interpretation for our theta or gamma. Oh, well, now I in the previous slide it was gamma, sorry. But yeah. And so that's available. And so from that information, we can actually see that, for example, for k is bigger than 2, well, I sigma 0k polynomially simulates wk0 plus I rt22 plus I sigma 0k for all pi1 consequences. So it was, the previous basis theorem discussion showed that it's pi1 conservative, and actually there's a canonical way to convert the proofs between them. And similarly, if k is bigger than 3, then together with rt2, the same thing holds. And now with b sigma 0.03 or above 10. The similar thing for k is bigger than 3 for rt22 is also true, but that's just included here, so I didn't mention. But yes, so all the previous pi1 conservation results can be actually upgraded to a polynomial proof transformation. And for the partial conservation proof using indicator style discussions or the ordinal analysis style discussion, that's also available. There's a reasonable Fawcett interpretation for that, for indicators. And then we may say that I sigma 01 polynomially simulates wk0 plus rt22 for pi3 consequences. That's possible. However, this is not always, I would say. There's an interesting counterexample. For the wk0 star, without sigma 1 induction, just over v sigma 1 plus exponential. wk0 star plus rt22, it's still pi3 conservative extension of the first order part of WK0 star, which is isolated as an B sigma 01 plus exponential. So that's pi3 conservative, and conservation proof looks like almost similar to the above one. I mean, well, actually easier than that. But there's no polynomial simulation in this case. And it actually has a, well, super exponential speed up. So never be polynomial. And so I said that WK0 plus RT22 is pi04 conservative over B sigma 2, but it's still open whether there is a polynomial proof simulation for pi4 consequences or not. That's still open. And okay, so combining everything, then we get this kind of situation. So the original power conservation question actually, actually also rephrased using the terminology of polynomial proof transformation. And then so RT22 plus WK0 plus B sigma 2 is power conservative over B sigma 2 if and only if, well, it's pi5 conservative, or, well, pi5 conservative means we already have a basis theorem. So basis theorem provides a polynomial proof simulation. So conservation result is available. If conservation result is available, then it has to be polynomial way. And always the counterexample is this one, basis theorem for RT22. And if we add, well, I mean, well-foundedness principle, if we add well-foundedness principle to the whole level up to epsilon 0, then it's all actually true statement. But we can add, level by level, we can add some well-foundedness principle for some primitive recursive ordinal alpha. And then if alpha is big enough, then everything is just true. But I mean, in general, we can characterize in this way for together with some well-founded assumption.
It's a little bit. You really have to go looking for it.
Right.
So what is alpha here?
So alpha is just any primitive recursive ordinal.
Any will order.
Yeah, but it's bigger than epsilon 0, it collapses just the. Like omega to k, where order is omega to k, that's what I expect. Not omega to k, sorry, omega sub k, I mean, k star of omega. Right. That's the general. I mean, that's the.
At least omega to be omega.
Yes. Yes. Right. Okay, so I'll try to close my talk. But, well, so actually, so the question is, okay, now the current situation for this main question is now, okay, I mean, together with I sigma 2, or well-foundedness of epsilon 0, or BME actually, it's the kind of a known upper bound for this conservation. And indeed, the killer example is like basis theorem for RT22. And also, we can rephrase a question by, I mean, speed up type of question. I mean, proof length question as well. And typically, so I said like here, whether there is a polynomial proof transformation between RT22 and B sigma 2 for pi4 consequences. But if the answer is negative, like this, then it also means that it's not power conservative, for example. So several different approaches may help for this main question, but it's still open. Okay, that's all. Thank you.